We will continue with our discussion of basic converters. Remember that in the last lecture we had talked about 3 converter configurations which we could get out of the inductive switch cell. Now, we will just try out the capacitive switch cell and see what we get. So, on your screen now is the basic capacitive switch cell with an inductor connected to the pole of the SPDT. Now, if you recall that we had put a criterion that for the capacitive switch cell at least one of the nodes out of T1, T2 and P, at least one of those nodes must be connected to a current stiff element. Now, the obvious you could choose any one of these, but the obvious one to select would obviously be the pole of that SPDT. So, that is what we have attached it to, and let us see what is the most obvious connection that we get. So, that is the corresponding converter. I will just draw the converter circuit separately. Okay, so we have not really said anything about the load yet. So, we will so, this is the extra new element that we get in the circuit. Otherwise, it has a very eerie kind of a similarity with the structure of the buck boost. Now, convince yourself that for any other orientation of this capacitive switch cell, any other orientation would give any one of the previous basic converters that we had seen. So, just to make sure that we do not have any confusion, so that would be P. And this is one of the possible configurations. So, if this whole if this entire SPD capacitive switch cell is turned clockwise by 90 degrees. So, this is the corresponding configuration that you would get. and you can convince yourself the other, if you instead of turning it clockwise, if you turn it anti-clockwise and start forming the other circuit, it would look exactly like the buck configuration. Here it exactly looks like the boost. So, that is why we are not looking at all the possible orientations of the capacitive switch cell. This what we have shown here out this particular converter configuration is the only different configuration apart from what we have already seen previously. So, this is the one which we will concentrate on now. Let me erase this part, because this really does not interest us. We have already seen how this converter operates, we have seen its steady state behavior as well. Okay. So, shall we go about doing the similar exercise what we did for all the other converters, right. So, let us mark the inductor voltages, we will call it VL, and if you notice that when in the position T1, which we will just arbitrarily call the duration to be T on, and in the position T2, the duration in T2 will arbitrarily call T off. So, VL is equal to Vg when the switch is in position T1, and when the switch is in position T2, VL is equal to, well, VO. So, now you can guess, I am not going through the whole exercise as we had done before, but from the similarity with the buck boost converter, I can now straight ahead write that AV, which is the voltage gain, I do not have to do anything else in order to go, the moment the inductor voltage expressions are very similar, the voltage gain is going to work out very similar. So, we do not need to go into the detailed process of it. Okay. So, apart from the boost, the buck boost and the buck, the three base, this is the fourth basic converter, which is known as this is pronounced as chook. So, this converter configuration was proposed by he was one of the pioneers in modern power electronics, and he was from Caltech. So, it was his innovation, and now it is obviously treated as one of the basic converters. Now, having said that, let us now look at some more intricacies of the operation and what are the consequences of the switching operation of the power electronic converters. Okay. So,